This is a video for how to go about doing calculations for questions 8A, 8B, 11A, and 11D for activity 2.1.1. Tolerate this for your engineering class. I would like for you to note that for activity 2.1.1, we are in the distance learning activity. Now, in the info section directly below this video, you will find a link to make a copy of a Google Sheet where we will get some data and be doing some functions and some calculations within that sheet. Once you click on the link, it will ask you to make a copy, and on your screen you will see data as you see it here, and we will be doing some functions with this data here a little bit later in the video. But I want to go back to activity 2.1.1 and kind of walk you through a few things before we get started. Within the resources, there's a distance learning thing for types of tolerances. And just real quick, I want to go over the different types of tolerances. Now, the reason why we have tolerances is because variation is unavoidable in any part of manufacturing, and we want to specify how much tolerance or variation of dimensions we are willing to take in order for a part to work and function correctly. Now, there's three different types of tolerances, and the first one is a unilateral tolerance. And I'd like for you to note the dimension given is half an inch, 0.500, and it says, the value of this hole can only go up to 0.5004. It cannot go below that. So only the maximum amount of tolerance here is 0.004. So 0.504 up here at the top, but it cannot go any smaller than that dimension. Now, for bilateral tolerance, and go in two different directions. So this right here is, at about 1/4 of an inch. So it can go up 0.003 or down 0.003 in the size. So the total tolerance would be 0.006. You can look at it this way. It's 0.253 up or 0.247 down. And then what's the distance between those two numbers? That's your total tolerance. This is a bilateral tolerance, bi meaning it can move in two different directions. For limit dimensions, it'll actually give you the highest number and the lowest number. So in this case, the distance between these two numbers is 0.1 or 1/10 of an inch. So you'll actually see the limit value right here. So that is the different types of tolerances. And as we go back to the activity, when we scroll down, you're also going to see this additional practice worksheet. That's like a spreadsheet you're going to go through. I'm not going to get too much into that. Now, when I talked about variation, it's the difference between dimensions. So, large or small. So we just saw those three different examples. What's the maximum and minimum tolerance that we are willing to accept in order for the part to function correctly? So you'll note on this worksheet there's different types of tolerances, and we're trying to say is it a unilateral, is it a bilateral, or is it a limit tolerance? And I want you to notice that for A up here, it has a plus and a minus here, and this would be a bilateral tolerance for A. For C, this would be a limit tolerance, because I can actually see the limits here. Now for E, as an example, it would be unilateral because it can only go down a dimension, it can't go up. Anytime you see the zeros here, that would be uni, it can only go in one direction. That's an example of a unilateral tolerance. So as we get further into the assignment, we're going to start talking about interchangeable parts. And in a previous lesson, we had discussed putting holes in the trammel base of the trammel toy. And this right here is a view of the top of a trammel toy. And the trammel toy has, guide blocks that are here. And we also have these corner pieces. The corner pieces are what you see in green and in purple. And it gives the example of this purple piece here. And it says to measure this specific hole right here, because this right here is a metal pin that fits, and the metal pin is slightly larger than the hole on this purple piece, and the only thing that holds this corner block to our base with the holes in it is the dimensions of this metal rod that we see here. So within the curriculum here, they actually talk about taking a dial caliper and measuring the size of that specific hole. And in this case, the measurement here would be 0.229. Notice how it still has a zero here. We're at 0.2 of an inch. So we'd say 0.2, and then after that, about 0.29, maybe right a little bit between 0.28 and 0.29. That's what the size of that hole would be. So we'd be asking ourselves, what size pin should we have that could fit inside that hole and hold this corner guide block here into place? It can't be too big because it wouldn't fit and work. So we have to kind of start talking about the tolerances of dimensions. What's the maximum and minimum size of tolerances that we are willing to accept? Now, as we start getting into answering some questions as we go. We have to do some preliminary work with question 7, and they're giving you kind of the context here that you 3D printed 20 of these parts. PLA stands for polylactic acid, so we're going to say you printed them in PLA. You printed 20 of them, and you grabbed a dial caliper and you just grabbed a sampling of these and you measured the size of the holes. Now, as an example, in my class, I probably have about 50 of these. So just to give you an example, if I went in and just grabbed 20 of these and did the measurements of them, and I created a little chart, this right here is all of the measurements taken from 20 of these parts. This is just totally at random, just 20 parts. And we're going to calculate the average and the standard deviation, and we're going to be creating a histogram. Now, mean in this case is just the average of the numbers. We're going to find the average of that data set, and the standard deviation is a distance of a value in a population or sample, and this is a sample, from the mean value. I like to say this is the average distance from the average. So in this case, we're going to go back to our spreadsheet, and I have the data over here because I copied and pasted it out of the curriculum, and I took the liberty of taking this data and put it in a nice vertical row for us. It'll make life a lot easier as we go forward. Over here on the right, you're going to see that I have the words average, standard deviation, the max number for the largest number, the min number for the smallest number, and the range is the distance between those two numbers. We're going to do some functions. Now, if you're not familiar with spreadsheets at all, I want you to note that on your screen we see columns here that are vertical, and we see rows here that are horizontal. We'll also notice that if I tap on any cell in this case, these squares here are called cells, I am in cell I2. This might look like a lowercase l, but it's H-I-J-K, so we're in I, and I'm in cell I2. I don't need to necessarily double click. I can just tap on any one of the cells and start typing. And to do any functions or any calculations, if you will, in a spreadsheet, we need to hit equals. And we're going to start typing the word average. And I don't necessarily even have to type out the word. As soon as I start typing out the word average, you're going to see a little drop down menu here. I'm going to click on the word average, and you're going to see average. You know, I tell my students, I'm like, you know, this is kind of a frown face, if you will. We used to have before we had emojis, we were typing out, you know, smiley faces or frown faces. And this right here is nothing more than just a parentheses to say, what are you going to do the average of? And I'm going to click and hold down and highlight all of our data here on the left, and I'm going to hit enter. Now it's giving me some autofill suggestions in this case, and I'm going to hit X because I don't want them. The average number, add up all these numbers and divide by the number of numbers, is 0.23642. That is the average size of all of those whole measurements we did from the distance learning activity. Now for standard deviation, we went just of a sample. I'm going to hit equals, and I'm going to start typing STDEV. And what I want is just a standard deviation, you know, it says of a sample in this case. So standard deviation of a sample. We're going to click, we're going to highlight all the data, and we're going to hit enter. Now that is a very small number. A very, very small number, and that is a good sign. And what that's trying to say is that, you know, the average distance from the average of your measurement of this hole is only this small of a value. So we're not off from the average very much. We are really, really splitting hairs as far as how far we are from the average. That's a small value. But in some manufacturing, that could be considered too much of a deviation, where we need to start getting down into nanometers of deviation. We have to have absolute precision. Now, precision and accuracy matter, let's say, more so in some parts of manufacturing than others. For max, we want to find the max number. We're going to hit equals, and we're going to start typing the word max. I'm going to click on the word max, highlight my data. Excuse me here. Here we go. Screwed up here. Let off real quick. I'm going to delete that out. I don't have to highlight my data again. Let's come into here, highlight my data. I'm going to hit enter. Largest number is 0.204. 0.240, excuse me. I'm going to hit equals for min. Start typing min. I'm going to click on min, and I'm going to highlight the data. We're going to find the lowest number and hit enter. And then for range, I'm going to hit equals. And in this case, we're not going to write a function. We're actually kind of create our own. I'm going to tap on the max number. I'm going to hit minus. I'm going to tap on the min number and hit enter. 0.0071. Now, that is a pretty impressive small distance for the sizes of those holes. And you can get a pretty good indication of the accuracy of, let's say, your 3D printer. You know, I know that you can do things on a fast mode or a medium mode or, you know, an extra fine mode, and the extra fine mode should give you a much smaller deviation in 3D printing than, let's say, a super fast mode. It would just kind of go through it quickly. So that's one thing you can do with a 3D printer is, and when you use slicing software, if you want something super quick, you might not see, you know, as fine-tuned of an object as if you go on super fine or something like that. Now, this data gives us a lot of information just about that sample of the 20 blocks. again, we can find that we're pretty precise and we're pretty accurate because the range is a pretty small number and the standard deviation is a very small number as well. And also what's nice is, we're taking dial calipers, so human beings are measuring these and getting this data. And generally speaking, when you have people taking measurements themselves, it can be a lot different than, let's say, a laser taking measurements in industry or something like that. The next thing we need to do is to create a histogram. And a histogram is a graph of vertical bars representing the frequency of the distribution of a data set. So to create a histogram in Google Sheets, we're going to highlight the data and we're going to go up to Insert and we're going to go down to Chart. And when you go to Chart, it's going to automatically probably give you a line chart or something like this. Now I want a histogram, so I'm going to click on Line Chart and I want to come down to Histogram. And you'll see that it gives us a histogram, but it's not a very good representation of our data. I want a little bit more, specificity than this. So we're going to go to Customize and go to Histogram. And you're going to see bucket size, and you're going to see the outlier percentile. And what outlier percentile means, your largest and your smallest. Right now we're at a 0. There's 0 outliers here, really. We have one gigantic thing and one small thing. I want to have a better representation of the percentile of the outliers, and I'm going to go to 1%. And you're going to see it's going to shift this over to where it's going to look more like a little bit of an evenly distributed bell curve, if you will. I could change this to, I can go to, let's say, 5%. It might look a little bit more. We can get you as a teacher, and even depending on how specific you want the data, we can go into what percentage we want for the outliers. Now this looks like a pretty normally distributed bell curve. On the left side looks very similar to the right side, so I'm going to stay at 5% because this can help us as we move forward with looking at normally distributed data and also looking at how many standard deviations away from the mean what percentage of the parts we can find within certain standard deviations away from the mean. Now, this is a good, visual representation of our data. We can just look at this and get an idea of probably where our average is of being right down the middle. So let's go back to our assignment. We've made a histogram. We could do some unit conversions in this case, but we don't necessarily need to do any unit conversions. The accuracy and the precision of our data is, again, the representation that we saw in the numbers we crunched is, we have very accurate parts that are, pretty darn close to the average. And we also have, a very small range. Now we could say, the average, I want the average to be different. Then we can go in and talk about redesigning the part, maybe changing some of the dimensions within Fusion. To 3D print these parts, we would export them out of Fusion as STL files and 3D print them. I might need to go back in and change the size of some of these holes if need be to get my average to a different place in order to make the part function. Again, this all comes back to moving parts working together and functioning. So let's go back. For a normally distributed curve, I want you to notice that the left side and the right side are the same. This is what a normal distribution of data would look like, and kind of a, perfectly symmetrical thing of data. If it was asymmetrical, it would not be normally distributed. It's a perfect bell curve. Now, where we're getting into with data here is this is the empirical rule. And what the empirical rule is that one standard deviation away from the mean to the left and one standard deviation to the right, we would get 68% of our data. 2 standard deviations left, 2 standard deviations right, 95%. For 3 standard deviations left and 3 standard deviations right, we would get 99.7%. I think you can see how we could look at this data right here and find out what percentage would fall within our graph. So again, this is known as the empirical rule. Now that as we get in to 8 here, this is where we can answer a question. For 8a, it's asking us approximately 99.7% of the data points in a normal distribution will fall within the range indicated by mean plus or minus 3 standard deviations. You need to write a bilateral tolerance for that. So writing a bilateral tolerance for that would just be, equals, or I should say this, we can just write, I'm just going to type this out and say equals. I'm so used to writing functions, it's plus or minus from here, so plus or minus, and our standard deviation is 0.00169. We should say times plus or minus 0.00169. Let's do this real quick. One quick thing. Got a little bit ahead of myself here. Plus or minus that. Now this standard deviation right here, we said 3 standard deviations. So I'm going to go to the right of it, and I'm going to hit equals. And I'm going to tap on this number. I'm going to go times 3 and hit enter. I'm going to hit the X and get out of it. So this right here is 3 standard deviations away from the mean. So where I got ahead of myself is I just wrote 1. It says plus or minus 3 standard deviations, which would have 99.7% of our data. So 3 standard deviations in the plus or minus 0.050702. Let's just keep it there. That right there would be the answer for 8A. This would walk us through how to calculate that. Now we could actually write that out and make it look a little bit more like it would on a drawing sheet. Eventually we'll talk about how to put tolerances on a drawing sheet in Fusion, but this is what this would look like. So next question. B, use the mean and standard deviation to estimate the percentage of 3D printed corner guide blocks that will securely fasten to the trammel toy base plate with the dowel pin size that you selected. Now it's asking you which one of these pins, pin diameters would you select? And from a previous lesson we talked about which one of these holes do you think is a certain diameter, and this is kind of comes from a previous lesson, but we could say what percentage do we think would go fit with 7/32 of an inch. So one thing that you can do is if I wanted to find 7/32 of an inch, if I can come over here, let's get that out of the way, and I'm going to hit equals 7 divided by 32. I got 0.2185. Now 0 of those would fit in this area. It would be really, 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 really small. So let's go back into here. So 7/32, a quarter of an inch. If you chose that one, I can hit equals 1 divided by 4 is 0.25. That one might not be the best. If I want to do a quick unit conversion in Excel, it says tested dowel pin diameter 6 millimeters. If you chose that, we might have to convert that from millimeters to inches. So I'm just going with the number 6 right here, and let's just do a quick conversion. I can hit equals and start typing convert. I'm going to click convert, and I'm going to tap on the number to the left, and I'm going to hit comma, and I'm going to hit quote from quote, comma, quotations, IN. I'm going to close my parentheses and hit enter. So from millimeters, 6 millimeters, to inches, I did a quick calculation. Now 0.236. Now what percentage of those, if I take a look down here, 0.236, what percentage of those do I think would fit? Now are any of these going to fit within a 97th percentile is what it's asking. Use the mean and standard deviation to estimate the percentage of 3D printed guide blocks was safely fastened. So it says, what percentage of those do you think would fit? So I can go back here and just take a look at that. You can use whichever one you want. We could have said that 0 for, 0.25, wouldn't fit. So between the max and the min, which ones would actually fit? I'll let you decide which size of one of these blocks you think would fit. Now it says the measure corner guide block hole is 0.2365. I'll let you go through and pick whichever one you want, but that would be for B. Now for 9, we're just going to start talking about different types of fits. And there's little videos here that will show a pin going into one of these guide blocks. Now in this case, this would be a clearance fit because there's little to no friction when you put that in. That'd be a clearance fit. Now for this one right here, if you have to put any kind of a struggle through, as you turn, this one turns as well. They're trying to say that one's a 7/32 inch. That's a clearance fit as well. Now let's just take a look. Let's see here, 6 millimeters. This can give us some good data for up above too. As we take a look at these now, we want to see, is there any friction on that? You can turn that, but that one turns, but not quite as much. That's a little bit more of, let's say, a transition fit between the two. Now, if you have to really struggle to get any of them inside the part, now this one right here will not fit. It's a total interference fit. Cannot even fit that one through. So for 10, it gives you an example of a cylinder here. And we know this is a cylinder because we see that center line going down through the center. This over here is a hole, and these are known as section lines. I know this is a hole because it looks like a hole was cut through a part, and these section lines tell me where material was cut. So in this case, I have a cylinder going into a hole, and it gives me a limit tolerance, 10 maximum, minimum 9.92. Now over here we have 10.25 as a maximum for the hole and a minimum of 10.15. Those are the diameters for the hole. So if we take a look at this right here would be a clearance fit because the hole is way bigger than the cylinder that's going into it. This one right here, in this case the hole is smaller than the cylinder going into it, so there would be an interference. The next one we can say is a transition fit because these are pretty darn close, probably can pop this thing through a little bit with some friction to it. These would probably mate, if you would. They would actually probably be able to go together with a little bit of force. That would help us. So I'm going to skip over check for understanding. Let's go down to this. We're going to allow it, we're going to skip over this for now. So for 11A, what type of fit is shown in figure 11? 10 and 9.92 here, 10.25 and 10.15. This would be a clearance fit because this cylinder would fit through this hole very easily. What is the tolerance for the shaft diameter in this case? So that for the shaft diameter is this, the tolerance is a limit tolerance. Now the question we have to answer is if the design of the assembled parts requires the shaft is sized such that the actual clearance between the shaft and the hole is greater than 0.3, will the current shaft design meet your requirement? Explain your answer. And what we're saying is that, if this, would this fit or not? So the assembled parts have to be able to be held together. And you're trying to say the actual clearance between the shaft and the hole is never greater than 0.3 millimeters. Would it meet the design requirement? So I would go ahead and you can explain your answer yes or no in this case. Do you think it would be able to fit or not? I think that you could say it might meet the requirement because it could be a transition fit. I'm going to let you go ahead and answer that yourself. I was kind of going to go back just real quick and just to show you again how to do conversions in Excel. Now, if you look at this function right here, this will help you greatly moving forward because with this 6 as an example, if I just want to change that, it's automatically going to adjust for me. So as you go back and maybe answer that question, I can actually go from some of these millimeter dimensions and change them to customary measurements. So this has been a video for how to go about understanding how to do some of the calculations for Activity 2.1.1 and also how to do some Google Sheet functions and create a histogram to help guide you as you find your answers to this assignment.